today, what I really wanted to do is go a little bit of a deep dive into electrode double layer structure and the thermodynamics of that and the picture of these interfaces, because they're really critical in essentially everything that we do in LiSA involves an electrified interface. And, you know, the fundamental picture of this has been developed by physical chemists over the last sort of century, really. And there's a lot of subtleties here that I think are important for us to understand. We talked a lot about electrochemical thermodynamics, and you know, we built this up in terms of basic chemical thermodynamics. And where we got to was this definition of the cell potential and particularly the electrochemical potential. So I want to go down to the electrochemical potential here, because that's really the key to understanding a lot of the stuff we're going to do now. Okay, so people have all seen the chemical potential generally, and it involves the partial differential of the free energy with respect to the number of species, typically constant pressure and temperature, and all other species. Now, the electrochemical potential, right? The electrochemical potential is different in that in this total free energy term, we add this electrostatic component, okay, ZQ phi or ZF phi. And this is really critical for electrochemical systems. So, you know, any sort of free energy, it describes a change in free energy describes the net thermodynamic reversible work a system can do. So we talked about that as well. And in an electrochemical system, electrostatic potentials substantially influence the total free energy the system has in it, right? So we need to include that term in there. And if the magnetic field was important, or if some other, gravitational potential were important in the total free energy available to do work, we'd have to include those terms too. But in electrochemistry, we typically include the sort of chemical potential term and the electrostatic potential term in the total free energy expression. So that's really the core of sort of how we think about and frame electrochemical thermodynamics that we went through. Some properties of the electrochemical potential. A few that come up over and over again is at equilibrium. If I have any given species in two different phases, if they're at equilibrium, they have to have the same chemical potential. If I have lithium in the electrolyte phase as lithium plus, and lithium plus in an anode or a cathode in a lithium-ion battery at equilibrium, they have to have the same electrochemical potential. And by equilibrium, I mean, if I have a chemical expression for a reaction that can occur, and it has a finite rate constant, so it's something that I'm including in my analysis, then I need to account for that in the equilibrium. Okay. So, we talked about some of the tricky concepts in electrochemistry, just happen to confuse everyone, like why you don't actually measure electrostatic potential. Usually with a voltmeter, you measure differences in electrochemical potential. It's the driving force in electrochemical systems are gradients in electrochemical potential. They're not gradients in concentration alone. They're not gradients in electrostatic potential alone. It's the combination of the two, typically for charged species in electrochemical cells. Measurements of potential differences, right? They're total free energy differences. If we want to decompose them into differences in activity, electric potential, that requires a model and assumptions. This equilibrium point is really important. The electrochemical potential of any given species must be the same throughout the system at equilibrium. If I have a chemical reaction, like if I have A plus B goes to C, I can write that the sum at equilibrium of electrochemical potential of A plus the electrochemical potential of B has to be equal to electrochemical potential of C, right? So they're at equilibrium. So if I make some more infinitesimal amount of C, then the chemical potential needs to be conserved. The delta G needs to be 0 for an equilibrium reaction. So I want to talk about double layer structure. So this is the basics, which you guys have seen before. So we typically define a few things. We define something called the inner Helmholtz plane. So if I have an electrode surface, say a solid surface, whether it's a semiconductor or a metal, right? And it's going to have some charge on it, some electronic charge. In this case, it's 1 negative, okay? It can interact with a solution in a variety of ways. Typically, there are some electrolyte ions that will specifically absorb. That means they've shed their solvent shell and sit on the electrode surface. So ions that do this notoriously are things like sulfate. They're strongly interacting ions, and they will typically absorb on an electrode surface. There'll be water, and that water will typically be relatively ordered relative to the random water in the electrolyte. It'll have some ordering at the interface. And then this is what we call the inner Helmholtz plane. goes right through the center of these specifically absorbed ions. Okay. And the outer Helmholtz plane, okay, and you guys have seen this too, this is the closest approach of the hydrated ions. And these hydrated cations, you see, they can't really get any closer to the electrode than the outer Helmholtz plane. One thing to notice immediately from this is actually really relevant to everything we do is the dielectric constant of water, right? So the dielectric constant of water in the bulk is what? 80, right? Relative dielectric is 80. But if you do a capacitance measurement, or you try to calculate the relative dielectric water of this water here at the interface, you often find a number more like 6. So the water, this interfacial water, is very different than the bulk water as well. So the double layer structure is critical as influencing electrokinetics. So if you think about, what kind of reactions are we interested in LiSA, right? So say you have a carbonate anion, right? Well, if that carbonate is specifically absorbing, and that's part of the reaction, the electrostatic potential drop of transferring a charge to that carbonate is very small. That's an inner sphere reaction. That's different from a sort of Marcus theory outer sphere reaction where you're tunneling through to the outer Helmholtz plane, tunneling through the double layer. So I'm going to go through some of this thermodynamics. The interface here, a phase, if I think about my electrode, right? I have my metal or my semiconductor electrode, and I have some distance here over which the concentrations of species are different than the bulk, right? And we're going to kind of define that as the interface region. And what we can say is, okay, I'm going to define a concentration at the interface in terms of an excess relative to the bulk. And then I can take the free energy, right? I can write the free energy of, say, the reference bulk system. I can just write the total differential. So that's basically, you take the differential with respect to a given parameter. So how does the free energy change with temperature times a small change in temperature? How does the free energy change with pressure times a small change in pressure, right? So this is sort of what you do in undergraduate physical chemistry or your first year graduate thermodynamics in graduate school. And so we do that for all the variables that are important in determining the free energy. And then we can do the same thing for our phase, our surface phase, okay? So if I do it for the surface phase, though, there's one new parameter, and that's how does the free energy change with the amount of interface, dA. So how does the free energy change with interface times a small change in interface. And so this is useful because this is actually the definition of surface tension or surface energy. So it's how much free energy it takes to create new interface. So this is going to be really key in understanding the thermodynamics of these interfaces is this thing, the surface tension, which is something you can look up for a lot of materials or calculate. Okay. Another thing we're going to make use of, and this is, one of our properties of the electrochemical potential, is that for any given species Ni at equilibrium, the electrochemical potential in the reference phase and the solution phase needs to be the same, right? That the magnitude of the electrochemical potential needs to be the same if they're at equilibrium. That's just one of our definitions. So, okay, so this is how Bard walks through this. So we can write then the difference in the free energy of the interface versus the reference bulk. And so that just has this surface term and this difference in the individual concentration. So that's just from taking the difference between these two expressions and introducing these substitutions. Okay, so that gives us an expression for how the free energy changes with area and number of species in the interface. There's a theorem called the Euler theorem, and it basically allows us to take this differential and rewrite it in this way. We say, well, okay, the total free energy of the surface, I can again write that as a differential with respect to area times the area, and plus the sum of the differential within the surface region with respect to all the species that are in the surface region times the amount of each of those species. So that's a mathematical equality that we're allowed to do. And so what's interesting here is that if I compare this equation, this total differential equation, to this previous equation I had for dg here, right? So if I differentiate this and compare it to what I calculated before, what you see is that these terms have to be equal to each other, okay? And so this is actually what's called the Gibbs absorption isotherm. So you've probably heard a lot about absorption isotherms in the past, and this is actually a pretty key equation. It's basically saying that changes to the surface tension are related to changes in the coverage of species, the excess coverage of species in this interfacial region, and the electrochemical potential of those species. So if the surface concentrations are different than the bulk, that's reflected in an interface energy, in the energy it requires to change the interface, right? And so this is one of the sort of fundamental equations that it's good to kind of have a feeling for where this comes from. Let's use this equation. So now I'm switching to a book by Schmickler. So if you're a physicist, you'll like this book, Schmickler and Santos. It's a very physical look at electrochemistry, and it's much more general than, say, Barton Faulkner, which tends to use more specific examples, and in some ways is a little easier to follow for chemists. Okay, so this is the same equation. So this is the absolute surface excess of species. This is the electrochemical potential of species. This is how the surface free energy is changing. You'll see why this is all important in a second. And then we use this thing called the Gibbs-Duhem equation. Basically, it just says that there's a compositional constraint on changes in electrochemical potential in a mixture. So, for example, if you have a mixture of components, there's only so many degrees of freedom. If you increase one chemical potential, you have to decrease the chemical potential of something else. So that's another one of these sort of fundamental thermodynamic equations. So again, he goes through some manipulations, but the final equation is going to be really useful. And what he does is he pulls out a reference phase. And this is usually the solvent. So that's this term here. That's just pulled out of this sum, and then this thing is rearranged. And this reference phase is useful because we're going to actually define this surface excess in terms of the solvent concentration, basically. So it's basically a relative excess of a given species versus the solvent. And the details, are not actually that critical at this point, but it allows us to simplify this expression. Okay. So what he does here now, he takes this Gibbs absorption isotherm. Here's the change in surface energy. We're going to use this to derive a lot of things, so it's important. Change in surface energy, and we're breaking it up into a bunch of different components. Okay, so this is that sum, and we leave stuff in the sum for things that are in solution, but we're going to pull out of this sum positive charge on the metal electrode. So he's written it here as Mz plus. What he really means is, in the metal, there could be lack of electrons, and that could give rise to positive charge in the metal, or there could be negative charge in the metal. That could be excess electrons. And so this is just that expression that we're pulled these terms out. And then, of course, there's these sort of neutral metal atoms that make up the metal surface. And those could be important too. He takes these terms, this sort of everything else part, not including the solution, everything in the solid, and he just expands them, right? And these electrochemical potentials, he's just expanding them because the electrochemical potential has a chemical potential plus an electrostatic energy term. So that's all he's doing here is expanding those and then rearranging them. So then once he rearranges these, you can define something called sigma. Now, sigma, of course, we know that's just the surface charge density. So that's charge per centimeter squared, for example. That's the net surface charge. And, he recognizes, of course, that the net charge in the metal is the positive charge minus the negative charge. E naught's the fundamental charge. And that this has to be balanced because the net system's electroneutral by the charge in the electrolyte. That's this term. So that's the sum of all charge species, the excess charge species, so just the excess charges in the electrolyte region. Okay, so that's the sum of the charge in the double layer, basically. So that's to balance the electronic charge. So we get this sigma term, and we make use of a couple more features of the electrochemical potential, which is, again, very central to all this. In equilibrium with constant phi in the metal, so phi is the same everywhere in the metal, you can say that the chemical potential is equal to that of the chemical potential of the positively charged metal plus an electron. That's this by definition of this equilibration process, right? And you can decompose the electrochemical potential of the solution species into a couple different terms here. And you add it all together, things cancel out in group, and you get this really nice equation. It's called the electrocapillary equation. From it, we'll see a lot of interesting features of the double layer. So what it says is that changes in the interface free energy can be grouped into electrostatic terms that depend on potential, right, and surface charge, and chemical terms that depend on stuff in this solution. Okay, so this is the electrocapillary equation. Here it is again. If I have constant chemical potential of all my species, right, then sigma, charge density, is just the change in surface energy as a function of applied bias. So this is actually really cool. So in the old days, people actually measured this a long time ago. So Graham did all the really key work here. And they had these systems where they'd actually look at electrowetting of metals by electrolyte, and they change the potential, and they just measure the amount of wetting, and they measure the surface energy. And what you can see here, and we'll get to why this is critical even now, is there's a potential, right? There's a potential at which the surface energy maximizes, and then at more negative or more positive potentials, the surface energy goes down. And it depends on the electrolyte you use. And so this is a lot of the work you've been seeing in CO2 reduction, right? People use this electrolyte or that electrolyte, and it actually has origins in this type of behavior, and we'll see why as we continue through this. Now, why do you think there could be a maximum with potential? What physically is, can anybody think of a physical explanation or a hypothesis why that might be? This maximum is what we call the potential of zero charge, is where there's sigma equals zero. Okay, right? That's where this derivative, right? This derivative, d gamma, d sigma goes to zero, right? So we're going to call that's the potential of zero charge. That's where sigma, there's no net charge on the metal. But if you move away from the potential of zero charge, you have charge on the metal surface. And by definition, like charge likes to repel each other, right? And the more charge you build up, that charge wants to get away from each other is a qualitative explanation. And it actually puts a force on the interface that tries to expand the interface, right? So it wants to expand the interface because the charge wants to get as far away from it as it can, itself as it can, the light charge, but the surface energy wants to contract the interface. So it's a balance between those two. And so what you see is you start applying potentials, the surface tension actually goes down. And it's because that additional charge is repelling itself and it's trying to create more interface. Well, if I take the second derivative of this, surface tension, at constant chemical potential, meaning constant concentrations, I get the capacitance of the electrode. So that's because capacitance, right? Capacitance is this d phi d potential, d phi d potential, right? So the capacitance measures how much charge is stored on the electrode as it's modulated by, some delta potential. So that's interesting because now we can measure interfacial capacitance. So here's an example of capacitance, probably mercury, in sodium fluoride, okay? You see a minimum in the capacitance. That minimum in the capacitance corresponds to the point of zero charge. The capacitance is the second derivative here. And it increases, the capacitance increases as you move away from the point of zero charge. And you could take this data and you could work out what surface energies are and things like that if you do concentration dependencies and things like that. Another interesting point is the potential of zero charge. The potential of zero charge is really critical because at this potential, if you're doing, say, electrocatalytic reaction, if you're at the point of zero charge, the water is going to be more free to move, less structured than, for example, if you're doing electrocatalysis out here, where you're far from the potential of zero charge. So the potential of zero charge is actually a very important concept in understanding sort of the interfacial structure under the conditions where you're doing catalysis. And so some of the things people say are like ions absorb, they move the potentials of zero charge. That affects sort of the free energy costs of reorganizing water and things like that. And that affects catalytic rates. So there's lots of arguments like this made in the literature. And this gives you a framework to sort of start understanding this. Okay, so the potential of zero charge, actually it's correlated to the work function of the metal for bare metals. And that's just because of electrochemical potential equilibration, actually, the net degree of partial charge transfer and polarization that happens when you put an electrolyte next to a metal with different work functions. The concentration, the capacitance increases with salt concentration. So we see that here. This dip at the PZC disappears. So you actually have to go to very low concentrations to observe this potential of zero charge in capacitance measurements. And I mentioned this as a higher work function, you get more electronet, means a more electronegative electrode and a more positive PZC, meaning you have to push the electrode more positive to sort of compensate for the negative charge that it accumulates just when it comes into equilibrium with the electrolyte. And this stuff is still being actively researched. So here's a very recent paper from Mark Koper. They still don't understand platinum 111 and exactly what's going on in this double layer region and where these capacitance minimums are and things like that, and how to relate that to the specific structure of the double layer is absolutely critical for all this catalysis.
What is it about high concentration of the electrolyte that means you can't get a zero charge on the surface?
Well, no, I think you could still get a zero charge on the surface, but you just can't easily measure it. This is typically called the compact layer, right? So here's our capacitance of the compact layer. And then there's this diffuse layer capacitance here, CD, C. And, capacitances add in inverse. So C total equals 1 over CH plus 1 over CD. So the smaller one dominates the capacitance of this whole thing. And if you're at a high electrolyte concentration, you have so many ions, and we'll see this in Poisson-Boltzmann distribution and how we have to modify that with this Stern modification, that as a function of bias, this layer essentially doesn't change, and it's all sort of small changes in the diffuse layer, but you're not sensing that. If you only measure this layer, you don't see the point of zero charge. You can't see that large dip because you have essentially this constant capacitance that's dominating the capacitive response. But if you go to very low concentrations, then the diffuse layer becomes more important in determining the overall capacitance of the equivalent circuit. The Helmholtz model is the simplest model we can put forward for the double layer. And you'll hear about the Helmholtz potential drop. People will use that term all the time. Basically, we're just treating this as a double layer capacitor, right? One sheet of charge in the electrode, one sheet of charge in the electrolyte. So this surface charge, this is just the equation, right? For a capacitor, the surface charge is just related to the voltage across the capacitor, the distance between the plates of the capacitor, the relative dielectric constant, and the E naught, the dielectric constant free space. And so we can define, right, the first derivative of sigma with voltage, that's the capacitance, and that's given by this term. And so this, predicts a constant CD, which is not what we observed experimentally, right? But it's a model that can be used in certain situations to understand the double layer. A more sophisticated model is called the Goi-Chapman theory, Goi-Chapman model. And this is, obviously, we know this, right? Just the chemical intuition tells us if I have a wall of negative charge, all the positive charge is not going to be right next to the negative charge. So why is that, by the way? Why would not all the positive charge not be right next to the negative charge? Why is there this diffuse region? Why doesn't it all just line up right next to the negative charge? What do you guys think? Let's think of another example, okay? What if I just had a bunch of molecules and I align them all up at a surface, okay? Don't worry about electrostatics at this point. And then there's this big box that was completely devoid of all these molecules. What would those molecules do? Let's say they were argon molecules in a row. What would they do? They would diffuse away from the wall, right? And they would fill all space, right? They would be randomly distributed in this box, right? Like there's no reason, there's nothing holding them there, right? So, okay. But here, this is not any different, except now there's something holding them to the surface. And so it has to do with what's the energy of something holding it in place versus what's the entropy gain by letting these things diffuse out into the bulk, right? And there's some competition between the two. And that's what's going to give rise to this sort of diffuse layer. So that's what we're going to do next. So I wanted to sort of introduce that and let you guys sort of searching in your brain to think about the underlying physics here. So we can model this. So I have an electrode, and that electrode will have some charge on it, okay? And it's going to be compensated by charge in the solution that's going to make up the double layer. So this is the sort of double layer region. And what Goi-Chapman did is they said, well, I can split the double layer up into a series of lamina. So this is going to make this a one-dimensional problem, each with thickness dx, right? And I can say, well, if I have some bulk ion concentration, and I know there's some potential distribution in the electrolyte, the electrostatic potential is a position of X in the electrolyte, I can write via an approximation. I can say, well, the concentration of those charged species at any given point, any given lamina, function of position, is going to be the bulk concentration times this term. So what does this term remind you guys of? What is this? Where's this come from? Looks like an Arrhenius expression, right? So what is an Arrhenius expression usually used to represent? What is that? What do we usually use an Arrhenius expression to represent? For overcoming a barrier, right? Okay. So let's think about that, right? So imagine here, this is the electrostatic energy, right? The charge number, Z is the charge number, E is the fundamental charge times the electrostatic potential. This is an energy. This is thermal energy, right? So this is a Boltzmann factor. If you think about Boltzmann factors, I have a bell-shaped curve. And if I want to know sort of, this is a probability distribution as a function of energy of some molecules, say they're ions, right? And I want to know how many ions are in a given lamina. I could say, well, what fraction of the ions have enough energy to go above some activation energy, if you want to think about a thermal process, or in this case, imagine I'm talking about, there's some negative charge here, and I'm talking about the location of positive ions in these lamina. They're gonna fill an attraction, right? So there's going to be an accumulation, whereas if I am talking about negative ions, there's going to be a depletion in this region because of the electrostatic energy that's modulating the bulk concentration. This is just a Boltzmann term. It comes from the statistical nature of things. There's going to be, for any given series of energy levels, like in chemistry, you often learn about a series of energy levels, and you think about the occupation of these energy levels being determined by the Boltzmann factor of each energy level, right? Which is given by EA energy over KT, right? E the negative energy over KT. And you can think about these lamina, each as having different electrostatic energies, about that being sort of the energy that goes in the Boltzmann factors. That's all this is. It's the same stuff you've seen since general chemistry. And then we can write the charge density then. That's just the sum of all the charge species. So Z is the charge on any given charge species, N is the number of charges, E is the fundamental charge. This is just like add up all the pluses and minuses, and what's the net charge density? It's going to depend on X. And we can just plug in for any given species the expression for Ni, right? The number of species. And then we have this sum over the all charged species, the bulk concentration, and the Boltzmann factor for every species. So some are going to be enhanced by being close to the electrode, and some are going to be depleted. So this is pretty easy to solve, this differential equation. So this is the Poisson equation. So it just relates the charge density to the electrostatic potential, the second derivative of electrostatic potential. You can think about this, if you integrate charge density, what you typically learn in freshman physics, right? If you take the integral of charge density, you get electric field. The integral of the electric field is electric potential. That's kind of what this is saying. If you integrate this twice, right, I'm going to have potential. If I integrate charge density twice, I get potential. That's all this is saying. And so we can write this equation. We can just plug in for the charge density, which we just solved. And then we can just note some simple mathematics so we can, rewrite the second derivative in this way and get a differential equation that's a lot easier to integrate. So we can integrate that once. That gives us one solution. It turns out you have to solve it for the specific species that you have, the specific I's. So if you have like sodium chloride or calcium sulfate, these are called 1-to-1 electrolytes, one cation per one anion. So this is the actual solution for that case of 1-to-1, but the details are not that important. You see exactly where it comes from. It comes from this competition between thermal energy wanting to spread all the species out over space, but the fact that some locations in space have different energies, electrostatic energies, in other locations. Okay, so we take this expression, separate and integrate that expression, and you basically get this, which is the electrostatic potential as a function of the electrostatic potential right at the electrode surface. And it has these tan H terms, which we'll get rid of in a second in an approximation. And then we define this thing kappa. Kappa is 1 over LD. So LD, you guys have probably heard about this, the Debye length, right? So what does the Debye length usually mean to you guys if you think about Debye length? Typically think about it as a screening length. So like, things that have a lot of mobile ions, mobile charges, I should say, metals, right? Metals have very, 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 very small Debye lengths. Dilute electrolytes can have Debye lengths on, 100 nanometers. Okay, so that's the screening length. So this kappa essentially relates to the Debye length. So that's a very important parameter. And what you'll notice is if this is small, this term here is small, you can basically see that the hyperbolic tangent of these terms are about equal to the argument, and you get a cancellation here, and you get this simple formula. So this is actually, what most people remember. So the electrostatic potential as a function of position is just given by the electrostatic potential at the interface times exponential decaying factor that includes the Debye length. So I could write x over LD or kappa times x, they're the equivalent, right? And so this is sort of the expression here. So this is the drop in the potential across the double layer. And what you see is that it works really well at small potentials, but as you start getting to large potentials, you start getting substantial deviations from this exponential behavior, and you have to use the more complicated form. So I guess I will just finish this up as you can integrate this Gouy-Chapman term, right? This charge term in the electrolyte, in the metal, and you get this is the capacitance. So we can actually find the capacitance of an electrode. And what you'll notice is it looks kind of like this part, but it doesn't really look like this part. And we have to fix that. So this Gouy-Chapman model is not quite right, okay? And the reason it's not right is because ions have a finite size. So what this Gouy-Chapman model allows for is as many ions as you want to pack right close to the surface where, at large potentials, you'll have a large free energy driving force to pack those ions, but they're too big. They can't actually fit. And this assumes that they're point charges. We never talked about the finite size of the ions. And that's why, it works well for dilute electrolytes where the double layer is mainly diffuse. But when you get to concentrated electrolytes, you don't see this sort of nice parabolic Gouy-Chapman capacitance because the compact nature of the double layer, the fact that the ion has a finite size. And we'll take that into account next time, I suppose.